Hey everyone. As a robotics educator, there's absolutely nothing quite as thrilling as taking a concept that only exists on a computer screen and bringing it into the real, messy physical world. And today, in this explainer, we're embarking on that exact journey. We are going to transform a virtual robot simulation into functioning, tangible hardware. Basically, think of this as a crash course in creating life, from just silicon and wire. So let's dive right into this. Here is our ultimate real-world challenge. How exactly do you build an autonomous service robot, we're going to call it the ChefBot, that can confidently navigate the busy, chaotic hallways of a hotel entirely on its own? No remote controls, no humans steering it out of the way of some passing luggage carts. We're going to figure that out by looking at the foundations of Python robotics, ROS hardware, and SLAM mapping. By the end of our time together, you are going to know exactly what it takes. To completely demystify this whole system, we're going to use a really helpful biological metaphor. Here's our roadmap. We'll meet the ChefBot, then build its muscles in motors and drivers, give it some perception in senses and navigation, wire up the nervous system in microcontrollers and PCs, put it all together, and finally wrap up with a summary and pop quiz.
All right, Section 1. Meet the ChefBot and its hardware blueprint.
Before we buy a single wire or microchip, we really need to know what this robot actually has to do, right? Every single piece of hardware we select is dictated by 4 foundational requirements. The ChefBot needs a simple, cost-effective chassis. It has to feature autonomous navigation, meaning it drives itself. It absolutely needs obstacle avoidance to dodge static walls and unpredictable, dynamic humans. And finally, it needs a battery life that'll keep it running for greater than 1 hour. This right here is the blueprint for our entire build. Moving right along to Section 2, movement, motors and drivers. This is where we build our robot's muscles. To move around, we're using a differential drive system powered by 12-volt, 80 RPM Pololu DC gear motors, and they're attached to 90mm wheels. But, motors can't just run on their own. They need a driver. So we use the VNH2 SP30 motor driver, which relies on a genius little circuit called an H-bridge. Think of an H-bridge kind of like a system of dams and gates on a river. Open one set of gates, the water flows left to right, and the motor spins forward. Close those, open the other gates, the water flows the opposite way, and the motor spins backward. It's just a wonderfully simple way to reverse the flow of electrical current. Now, what's really fascinating is how we control that river of electricity using nothing but ones and zeros. A 1 means a switch is closed, and a 0 means it's open. By sending these simple binary signals to the 4 switches of the H-bridge, we directly command the robot's physical movement. A 1001 combination, the motor moves right. Send a 0101 combination, and it slams on the brakes. We are literally translating digital code into physical momentum.
Okay, Section 3 brings us to perception, senses, and navigation.
Having muscles is pretty useless if you're driving blind, right? We have to give our robot some senses. Now, our wheels have encoders to count how many times they rotate, which is great, but wheels in the real world constantly slip on hotel carpets or smooth tiles. If we only trust the wheels, the robot's going to get lost fast. That is exactly why we add an IMU, specifically the MPU 6050. It acts as the robot's inner ear. It uses an accelerometer and a gyroscope to feel the actual movement and dynamically correct those nasty navigation errors. But wait, the inner ear only tells the robot where it is, not what's sitting right in front of it. Enter the HCSRO4 ultrasonic sensor. This incredibly cheap 5-volt ping sensor acts as the robot's rapid collision avoidance reflex. It just bounces high-frequency sound waves off objects right in its path, measuring distances from 2 centimeters out to 4 meters. Basically, it's the robot's flinch mechanism so it doesn't step on your toes. For higher-level navigation, the source material reveals this brilliant, budget-friendly hardware hack. Industrial laser scanners for mapping are, well, they're ridiculously expensive. But an Xbox Kinect or an Asus Xstation Pro uses an infrared projector and camera to generate rich 3D point clouds of the environment. By processing that point cloud data in software, we literally trick the robot into thinking it has a $1,000 laser scanner, giving it the power to see the entire room in 3D.
Next up is Section 4, microcontrollers and PCs. It is time to build the brain.
Now that we have muscles and senses, we need a central nervous system to route everything. For the spinal cord of our robot, we are picking the TivaC LaunchPad over a standard 8-bit Arduino. Why? Well, because the LaunchPad racks a 32-bit ARM Cortex-M4 running at a blazing 80 megahertz. When a robot is moving, it needs incredibly fast interrupt handling to react to obstacles instantly. Plus, the LaunchPad has the massive number of hardware timers and outputs required to smoothly pulse our motor drivers while juggling all that incoming sensor data via the Inertia IDE. But remember, the LaunchPad is just the spine. The big brain of the operation is this Intel NUC mini PC. Now, you might be wondering, why not just use a Raspberry Pi? Well, remember that Kinect we're using as a virtual laser scanner? Processing millions of 3D data points and running advanced ROS SLAM algorithms, that's simultaneous localization and mapping, requires serious computing horsepower. The Intel Celeron processor and 4 gigs of RAM in the NUC give our robot the cognitive power to actually think and map its world in real time.
Almost there. Section 5. Putting it all together.
Let's look at how the brain, the spinal cord, the senses, and the muscles all connect to the biological heart of our robot, the power supply. We need a battery that can pump life to everything at once without just dying in 10 minutes. Let's do a quick reality check on the math. Our big brain NUC draws 3 amps, the Kinect draws 1 amp, the motors draw 0.7 amps, the sensors sip less than half an amp. To comfortably cover this continuous draw and hit our blueprint goal of over 1 hour of operation, we select a 12-volt 9-amp-hour Li-polymer battery. It is the absolute perfect light-weight heart for this whole system.
And this brings us to the entire flow of our robot's anatomy in action. Picture a signal traveling through the system. Step 1, the Kinect and ultrasonic sensors perceive a wall. Step 2, the LaunchPad spinal cord receives this data, using level shifters to safely bridge the 3.3-volt and 5-volt signals. Step 3, it shoots that data up the USB to the NUC brain, which updates its internal map. Step 4, the brain commands the spinal cord to turn. And Step 5, the LaunchPad pulses the motor driver, the H-bridge flips, and the muscles steer our robot to safety. It is a beautiful dance.
Which brings us to our final stop, Section 6, Summary and Pop Quiz. Let's do a rapid-fire review. We've successfully designed an incredibly cohesive anatomy for our autonomous robot. The Pololu motors and H-bridges form the muscles. The Kinect, IMU, and ultrasonic sensors act as the complex senses. The TivaC LaunchPad routes signals like a spinal cord, while the Intel NUC does the heavy cognitive lifting as the brain. And finally, that 12-volt Li-polymer battery beats steadily as the heart. It all comes together perfectly. So, to leave you thinking today, here is your pop quiz. What specific piece of everyday hardware did we use to mock the functionality of a super expensive industrial laser scanner, allowing our robot to generate a 3D point cloud for SLAM mapping? If you said the Xbox Kinect, you absolutely nailed it. It's brilliant, budget-friendly engineering hacks exactly like that which make robotics so utterly fascinating. Thank you so much for joining me for this explainer on ChefBot hardware. So what real-world problem are you going to build a robot to solve next? Keep building, keep learning, and I'll see you next time.